Okay, let's talk about something you've definitely felt before, but maybe never really thought about. Why in the world does hand sanitizer feel so cold on your skin, even when the bottle's been sitting at room temperature all day? Today, we're going to play detective and dive into the invisible science behind that everyday chill.
You know the feeling, right? That sudden, almost icy blast when you rub it in. The bottle isn't cold, your hands aren't cold, so what is going on here? What's the secret?
To solve this little mystery, we need to bring in our main suspect, a process you probably remember from science class called evaporation.
Right, so evaporation is what scientists call an endothermic process, which is really just a fancy way of saying it's a heat thief. See, for a liquid molecule to break free and turn into a gas, it needs a little kick of energy. And where does it get that energy? Well, it steals it. It literally steals thermal energy from whatever it's touching, which, in this case, is your skin.
So this is the crucial part. The speed of that evaporation is everything. A puddle of water on the sidewalk evaporates pretty slowly, right? It doesn't make the pavement feel cold. But a liquid that vanishes in a flash, that's going to steal heat way more aggressively. And that's what creates that intense chilling effect we feel.
Okay, so if fast evaporation is the crime, we need to meet our two main suspects. Their molecular behavior is the key to cracking this whole case wide open. On one side, you've got the alkanes. Just think of these as pretty balanced, symmetrical molecules. But on the other side, we have the alcohols, like the ones in your hand sanitizer. These guys are a little lopsided because they have this special attachment, an OH group, that gives them a slight electrical charge. And as you're about to see, that little difference changes absolutely everything.
So why do these tiny molecular differences matter so much? Well, the answer lies in these invisible forces that act kind of like glue, holding all the molecules together. Scientists call them intermolecular forces, or IMFs for short, and they basically determine how easily a liquid can escape and evaporate.
So let's stick with that idea of a molecular glue. Alkanes, they're held together by the weakest kind of glue there is. It's called London dispersion forces. Just imagine a really brief, flimsy handshake. But alcohols, they have that same weak force plus much stronger ones, including a real powerhouse called a hydrogen bond. That's not a flimsy handshake. That's like a firm, lasting grip that really doesn't want to let go. Okay, so how can we actually measure the effect of this molecular glue? Well, we can stage an event, a kind of competition, the Great Evaporation Race, to see these forces in action.
The setup for this race is actually wonderfully simple. You just take two thermometers, wrap their bulbs in a little bit of paper, and then soak one in an alkane and the other in an alcohol. Then you pull them out at the exact same time and just watch as the temperature plummets while those liquids evaporate away.
By tracking how fast that temperature drops, we're not just watching a thermometer get cold, we are literally measuring how strong that molecular glue is. The faster that temperature plunges, the weaker the glue must be, and the faster the liquid is escaping.
All right, the race is over, and the results are officially in. Let's see which of our liquids created the biggest chill and unmask these invisible forces.
So, who do you think won the race? Which liquid was the master escape artist? Well, the data from the thermometers tells a very, very clear story. The one that caused the biggest temperature drop was the one whose molecules could break free the fastest.
And this brings us right to our core finding, the big reveal. The winner, by a landslide, was the alkane. Its super weak molecular glue, that flimsy little handshake, allowed its molecules to evaporate incredibly fast, stealing a ton of heat and causing a massive drop in temperature.
Okay, this table right here is where it all clicks into place. Just look at the comparison between an alkane and an alcohol of a similar size. The alkane, with only those weak handshake forces, evaporates fast, giving us a huge temperature drop. But the alcohol, held back by that super strong, firm grip of its hydrogen bonds, evaporates much more slowly. And the result? A way smaller chill.
So, let's put all the pieces together, crack this case once and for all, and see why this all matters way beyond a cold thermometer.
And there you have it, mystery solved. That chilly feeling you get from hand sanitizer is the very real sensation of evaporation stealing heat right off your skin. And the intensity of that chill, how cold it feels, is dictated entirely by these invisible intermolecular forces that control how easily a liquid can turn into a gas.
But here's the really mind-blowing part. This molecular glue doesn't just explain why hand sanitizer feels cold, it dictates so much of the world around us. It's the reason water boils at such a high temperature. It's why honey is so thick and gooey. It's why oil and water refuse to mix. Seriously, it's one of the most fundamental principles in all of chemistry.
So the big takeaway here is that our physical world is just governed by these powerful, totally unseen interactions between molecules. And by asking simple questions like, hey, why does this feel cold? We can design these clever little experiments that actually make those invisible forces visible. Makes you wonder, what else around you is being shaped by a force you can't even see?